Good morning, good afternoon, good evening, dear participants of the conference. First of all, do you see and hear me well? Okay. So we'll talk about derivations and automorphisms of algebras, of infinite matrices, some important associative algebras of infinite matrices, and related Lie algebras. Let A be an associative algebra over a field, then it gives rise to the Lie algebra A minus, some definitions. Recall that linear mapping D is a derivation if it satisfies the product rule on the slide, and the commutation with a fixed element is an inner derivation of the associative algebra and of the related Lie algebra. And a linear transformation star of an associative algebra is called an involution if the conditions of the slide take place. Denote the subspace K A star of skew symmetric elements, and this subspace is a subalgebra of the Lie algebra A minus. Also denote by at sub j the restriction of the derivation at A to the ideal J of our algebra A, and denote the group of invertible elements of an associative algebra A with unit by the symbol JA. We call the conjugation by an arbitrary invertible element an inner automorphism of the associative algebra A, and hence of the Lie algebra A minus. And to every involution of an associative algebra with unit, we associate the scalar unitary subgroup of invertible elements such that the product of the elements A and A star is equal to a non-zero scalar. We will talk about the following classes of algebras of infinite matrices. So first of all, the associative algebra of all I cross I matrices over a field having finitely many non-zero entries. Sometimes these matrices are called finitary matrices, and notice that I is an infinite set. The algebra of finitary matrices gives rise to the general linear Lie algebra JL sub infinity, and the special linear Lie algebra S sub infinity is the commutator algebra of JL sub infinity. Remark that both Lie algebras and their representations attract considerable attention in the papers of Vera Serganova, Ivan Penkov, Karl Hermann Knepp, Ivan Dimitrov, and others. The algebra of finitary matrices is equipped with the transpose and the symplectic involution, so it gives rise to the Lie algebra O sub infinity of skew symmetric elements relative to the transpose, and to the Lie algebra of skew symmetric elements relative to the symplectic involution. In the following example, we consider the associative algebra M sub RCF for all our I cross I matrices over a field having finitely many non-zero entries in each row and each column, and notice that the algebra of finitary matrices is an ideal in the algebra of matrices with a finite number of elements in each row and each column. And the algebra of example 2 gives rise to the corresponding Lie algebra JL sub RCF and to the group of invertible elements of our algebra M sub RCF. The next example of the algebra of infinite matrices is the algebra MIF of I cross I matrices over a full def having finitely many non-zero entries in each column. Remark that if V is a vector space over a field F of the dimension which is equal to the cardinality of the set I, then the algebra of all linear transformations of the vector space V is isomorphic to our algebra MIF. And as before, we consider the corresponding algebra JL and the group of all invertible elements of such algebra MIF. And notice that this group is isomorphic to a group of all invertible linear transformations of the vector space V. The next example is the algebra of Jacobi matrices over a field F, that is Z cross Z matrices having finitely many non-zero diagonals. We also consider the Lie algebra, JL sub J. Such Lie algebras found applications in the theory of solitons, and they are found in papers of Boris Feigin and Boris Sigan. Finally, the last example is the algebra of all linear transformations of finite range of the vector space V over a field F, and the problem is to describe automorphisms and derivations of associative and Lie algebras of all our examples. First of all, we will talk about derivations of such algebras. First, an arbitrary derivation of the algebra of finite matrices is the adjoint derivation by an element from the algebra of infinite matrices having finitely many non-zero entries in each row and each column. Second, an arbitrary derivation of the algebra of all linear transformations of finite range is also the adjoint derivation by an element from the algebra of all linear transformations. And third, all derivations of the last two algebras, namely the algebra of matrices having finitely many non-zero entries in each row and each column, and the algebra of Jacobi matrices are inner. We present a very short idea of the proof of theorem 1, the algebra of finite matrices and the algebra of all linear transformations of finite range are locally matrix algebras. Recall that an associative F algebra is called a locally matrix algebra. The terminology is due to Alexander Kurosh. If for each finite subset of this algebra, there exists a subalgebra containing the subset, which is isomorphic to some matrix algebra. And in the paper, the link can be seen on the slide, we proved that the ideal of inner derivations of a locally matrix algebra is dense in the Lie algebra of all derivations in the Tikhonov topology. So for the derivation D of the algebra of finite matrices and respectively of the algebra of all linear transformations of finite range, there exists a sequence of derivations which are adjoint derivations by some elements A sub n from the algebra of infinite finitary matrices and respectively of the algebra of all linear transformations of finite range. Of course, we consider limits of sequences in the case of matrices of countable size, in uncountable case, we consider limits with respect to some Elder filter. Then we prove that the sequence A sub n converges to an element from the algebra of infinite matrices having finitely many non-zero entries in each row and each column, respectively to an element from the algebra of all linear transformations. Thus, we can prove the part 1 and part 2 of our theorem. And for proving the part 3 of the theorem 1, we notice that the algebra of finite matrices is an ideal that is invariant with respect to all derivations, and the algebra of Jacobi matrices is also an invariant ideal with respect to all derivations. Then we use the part 1 of theorem 1. The next problem is to describe derivations of Lie algebras of all our examples. In this regard, we would like to notice that Carl Hermann Knepp in 2005 described derivations of special Lie algebras as L sub infinity, O sub infinity, and P sub infinity over a field of zero characteristic, and he showed that every derivation of these Lie algebras is the adjoint derivation by an element from the Lie algebra of infinite matrices having finitely many non-zero entries in each row and each column. And Waldemar Golubovsky and Sebastian Jurek in 2018 proved that every derivation of the Lie algebra JL of infinite matrices having finitely many non-zero entries in each column is inner. The following theorem 2, part 1 and part 2 extends Knepp's description to an arbitrary field of characteristic other than 2. Theorem 2 let the field F has the characteristic not equal to 2. Then, first, an arbitrary derivation of the Lie algebra as L sub infinity is the adjoint derivation by an element from the Lie algebra J L sub RCF. Second, an arbitrary derivation of the Lie algebras O sub infinity and SP sub infinity is also a adjoint derivation, but by an element from the subalgebra of skew-symmetric elements relative, the transpose and symplectic involution, respectively. And finally, all derivations of the Lie algebras JL sub RCF and JL sub J are inner. Let us talk about the idea of the proof of theorem 2. In 1961, Herstein formulated the following conjecture. Let A be a simple associative algebra of characteristic other than 2, with the center Z, and either the center is 0 or the dimension of algebra A over the center is greater than 16, then an arbitrary derivation of the Lie algebra, which is square of the algebra A itself, and the Lie algebra, which is the square of the algebra with involution, extends to a derivation of the simple associative algebra A. More precisely, first, for an arbitrary derivation D of the square of the algebra A, there exists a derivation D tilde of the associative algebra A such that D and D tilde coincide on the factor algebra of the square of the algebra A modulo the center Z, and the second, for an arbitrary derivation D of the square of the algebra A with an involution, there exists a derivation that D tilde of the associative algebra A such that D and D tilde coincide the factor algebra of the square of the algebra A with an involution modulo the center Z. This conjecture was proved by Konstantin Beidar, Matthew Brichard, Mikhail Chebotar, and Wallace Smith Martindale thought in 2001. In fact, the problem for Lie algebras is reduced to associative algebras and to theorem 1. We'd like to remark that, in fact, Herstein formulated a much more general conjecture, and Beidar, Brichard, Chebotar, and Martindale proved a much more general result, but he formulated only what is needed for the proof of our theorem. What can we say about the automorphisms of our algebras of infinite matrices? First of all, we begin with some remark. In 1975, Nathan Jacobson described automorphisms of dense algebras of linear transformations of an infinite dimensional vector space containing a non-zero of linear transformations of finite range. This description immediately implies the following theorem. The following statement is due to Jacobson, and it solves the problem for associative algebras. First, an arbitrary automorphism of the algebra of finitary matrices is a conjugation by an invertible element of the algebra of matrices having finitely many non-zero entries in each row and each column. Second, an arbitrary automorphism of the algebra of all linear transformations of the finite range of vector space V is conjugation by an invertible linear transformation of vector space V. And third, all automorphisms of the algebra M sub RCF of infinite matrices having finitely many non-zero entries in each row and each column, and the algebra of infinite matrices having finitely many non-zero entries in each column are inner. Remark that the algebra of Jacobi matrices, the problem is open. We don't have a description of automorphisms of the algebra of Jacobi matrices. Some more definitions. An invertible linear transformation phi is called an anti-automorphism if the following formula holds on the slide. An anti-automorphism is an isomorphism of algebra A with its opposite algebra, and the transposed transformations are anti-isomorphisms of the algebra of finite matrices and of the algebra M sub RCF. And we notice that an involution is just an anti-automorphism of order 2. In order to understand automorphisms of our Lie algebras, we need to understand anti-automorphisms of the associative algebras first, because as we will prove later, that every automorphism of the Lie algebra either extends to an automorphism of the associative algebra or is the type on the slide where star is an anti-automorphism of the associative algebra. The following statement is due to Jacobson, and it describes the anti-automorphisms of the associative algebras. First, an arbitrary anti-automorphism of the algebra of finite matrices, and the algebra M sub RCF is a composition of the transpose and conjunction automorphism by an invertible element of the algebra M sub RCF of matrices having finitely many non-zero entries in each row and each column. And second, the algebra of all linear transformations of finite range of the vector space V, and the algebra MIF of matrices having finitely many non-zero entries in each column do not have anti-isomorphisms. So these algebras are not isomorphic to their opposite algebras. In 2001, Nina Stumme described automorphisms of the Lie algebras as L sub infinity, O sub infinity, and SP sub infinity over a field of zero characteristic. Following theorem 3 solves the problem for the Lie algebras as L sub infinity, O sub infinity, and SP sub infinity. It says that Stumme's description extends for an arbitrary field of characteristic other than 2. First, an arbitrary automorphism phi of the Lie algebra L sub infinity is a conjugation automorphism, or an automorphism of the type on the slide by an invertible element of the algebra of matrices having finitely many non-zero entries in each row and each column. And second, an arbitrary automorphism phi of the Lie algebra O sub infinity and respectively SP sub infinity is a conjugation automorphism by an invertible element X of the algebra of matrices having finitely many non-zero entries in each row and each column, where X multiplied by its transpose belongs to the field F on the slide. The following theorem 4 solves the problem for other examples of the Lie algebras of infinite matrices, namely M sub RCF, the algebra of linear transformations of finite range, and the algebra MIF. First, an arbitrary automorphism phi of the related Lie algebra of the algebra M sub RCF is a conjugation automorphism, or a conjugation automorphism of some special type by an invertible element of the corresponding associative algebra on the slide. And second and third parts say that an arbitrary automorphism phi of the related Lie algebra for linear transformations of finite range and of the related Lie algebra MIF of all matrices having finitely many non-zero entries in each column is a conjugation automorphism by an invertible element of the corresponding associative algebra on the slide. The idea of the proof of theorem 3 and theorem 4 is following. We again use the proof of Herstein's conjecture, but on automorphisms by Bidar, Brichard, Chibotar, and Martindale Their results are quite general. We will use only a small part of them that is directly related to our proof. Let A be a simple associative algebra of characteristic not equal to 2 with the center, and algebra A is not dimension more than 4 over center Z. If alpha is an automorphism of the square of the algebra A, then there exist mappings with some properties on the slide. And one more Kirstein conjecture on automorphisms by Bidar, Brichard, Chabotar, and Martindale. Let A be a simple associative algebra with an involution, and let K be the Lie algebra of skew-symmetric elements. Suppose that the algebra A has 0 center, then for an arbitrary automorphism alpha of the square of the algebra K, there exists an automorphism of the algebra A such that the formula of the slide takes place. So, from these results, it follows that every automorphism of our algebras either extends to an automorphism of the associative algebras, or every automorphism of our Lie algebras is of the such type on the slide where star is an anti-automorphism of the associative algebras. And of course, some open and unfinished problems. First, describe automorphisms and derivations of associative Mackey algebras and Lie-Mackey algebras. Remark that the class of Mackey algebras in an interesting class of algebras that includes all our examples except for the algebra of Jacobi matrices and appears in various classifications. Second problem, describe automorphisms of groups of our class of infinite matrices and in more general case Mackey groups, and try to describe automorphisms of the algebra of Jacobi matrices. Thank you for the attention.